Section 6. Today we're going to talk about the topic of geometric sequences. Now earlier on this semester we learned about arithmetic sequences, so just a little bit of a review to help you understand the difference. An arithmetic sequence was a sequence that had a common difference. So here's an example: -3, 2, 7, 12, ... So as you can see, they're going up by +5 in between each term. The first term was -3, second term was 2, third term was 7, fourth term was 12. So the common difference, D, was +5. Well, a geometric sequence doesn't have a common difference. Instead, it has what's known as a common ratio between terms. So here's an example of a geometric sequence. A geometric sequence such as 1, 5, 25, 125, 625. Going between the first term and the second term, the second and the third and the fourth, we're multiplying by 5. So instead of adding 5, subtracting 5, we're multiplying by that common ratio. Let's look at some examples. Determine whether each sequence is arithmetic, geometric, or neither. Now, if it's neither, then it won't have a common difference, nor will it have a common ratio. So looking at this first one here, 8 to 24, 24 to 72, 72 to 216, it looks like this is being multiplied by 3 in between each term. Now, if you're uncertain, just take a term like 216 and divide it by its previous term. When you do so, 216 divided by 72 is in fact going to give you 3. And then 72 divided by 24 is also 3. And finally, 24 divided by 8 is also 3. So there is a common ratio here, and therefore we're going to call this one a geometric sequence. All right, if we look at our next one here in 1b, we're going from 8 to 3 to -2 to -7. So here it doesn't look like there's a common ratio, but instead it looks like maybe there's a common difference between all of these, and it looks like indeed you're subtracting 5, or if you want to think about it as adding, you're adding a -5. So this is an arithmetic sequence. Now the difference visually between an arithmetic sequence and a geometric sequence is the difference between a linear graph, or a linear trend. In this case, it's decreasing at a constant rate here of -5. And over here, a geometric sequence, here's where you had one that's growing exponentially. So if you wanted to fit a line over these term points here, you would see exponential growth or decay, or if you wanted to fit a line over an arithmetic terms sequence, then you would see a linear function. All right, in example 2, we want to write the next 3 terms of each geometric sequence. So before we do that, we need to figure out what the common ratio is. The common ratio can always be found by taking the second term and dividing it by the first term. So remember, these subscripted numbers represent position numbers, and our position numbers here in the sequence. So we're going to take 324, our second term, and divide it by 972. That's going to be reduced down to 1/3. So our common ratio here, or our common multiple here, is going to be 1/3. So if I take 36 and multiply it by 1/3, I'll end up with 12. 12 times 1/3, I will end up with 4, and 4 times 1/3, I'll end up with either 4/3, or in decimal format, that's 1.3 repeating. Again, if we were to plot these points on a graph, you would see this is going to be a discrete graph, and it's going to be this exponential decay type of a graph. In example 2b, we've got 7, -14, 20, -56. Now this is kind of an interesting one here. It looks like it's alternating from positive to negative, negative to positive, and back to negative again. So let's start by finding our common ratio by taking that second term and dividing it by our first term. That's -14 divided by 7, and that's going to give us a common ratio of -2. So here you're multiplying by a negative number, and that's what causes it to alternate between positive and negative. The next number I get is by taking -2 and multiplying to -56, and that will give me a positive 112. positive now times a negative, so positive 112 times a negative 2 is now going to give me negative 224. And then my next one here will be, again, back to positive 448. When it comes to graphing a geometric sequence, remember all sequences are discrete. They're discrete because they're just plotted of the term values, and each one of those points is made up of the position number n and the value of that sequence at that position. So our first position here is 6, second is 12, third is 24, 448, and our fifth position is 96. So in this case, we are going to plot the point 1 over and 6 up, 2 over and 12 up, 3 over and 24, 4 and 48, 5 and 96. So you can see how if you were to fit a line over this, this is growing exponentially, and this geometric sequence here looks like they're growing by multiples of 2. Alright, let's flip on to our back page here for 6.6 geometric sequences. And it says here, write an equation for the geometric sequence. Alright, here is our generic form. The equation for a geometric sequence. A sub 1, remember, is your first term. R is your common ratio. And n simply represents your term number. Alright, it says write an equation for the nth term of a geometric sequence. Start off by identifying what that first term is. We'll call this g sub 1 is equal to 3. Then let's identify what our common ratio is here. It looks like if we take our second term and divide it by our first term, that will be 12 over 3, and that gives me a common ratio of 4. Next up, we're just going to write our equation now. We're just going to follow this template here. The template says you can write by saying a sub n, okay, any term in the sequence can be found by taking your first term, which is 3, multiplying it to your common ratio, 4, and raising it to the n minus 1. Now I can find any term in the sequence simply by plugging in the n, or the position number that I want to find. And that's what we're going to do for the next part here. It says to find a sub 10. So a sub 10 would be the 10th position in this sequence, and I can find that by taking 3 times 4 to the 10 minus 1. So following your order of operations, we need to simplify the 10 minus 1 first. This is 3 times 4 to the 9th. Next up, we need to do our exponents, 4 to the 9th, and then we'll take that result and multiply it by 3. When we do that, we're going to end up with 786,432. Alright, in example 5 here, we are clicking the zoom in button on a mapping website, and it halves the side length of a square map. After how many clicks on the zoom in button in the side length is the side length of the map 5 miles? Alright, so just following our sequence here, we're just going to continue this out. It's simple enough that we can find this by hand as long as we understand the task. Remember, we are halving the amount. We're going by multiples of 1/2. So 160 times 1/2 gives me 80. 80 times 1/2 gives me 40. Next up, we would have 20. Half of 20 is 10. Half of 10 is 5. So continuing in this pattern, it looks like we would be at 6 zoom in clicks to get to a map that has a side length of 5 miles.